Good afternoon, everyone.
Good afternoon. How you doing?
Hi, Rory. Thanks for being here. All right, welcome to the second edition of our Gold Science Communications webinars. My name is Tom Mason, and I am the Communications and Outreach Manager at the University of Colorado Boulder's Laboratory for Atmospheric and Space Physics. And I'm the communications lead for the NASA Gold mission. Thanks everyone for being here this afternoon and maybe this evening, depending on where you're joining us from. We're glad you're able to be here and take the time to join us. I just wanted to mention before we begin, our next Gold webinar will be in the final weeks in May. I'm assuming it'll be on a Wednesday as well. Let's go ahead and get to our speaker today. I'm going to introduce Rory Barrett from LAST. Rory is a systems engineer here at LAST, and he's also the project manager for the NASA Gold mission, for which one of his main responsibilities has been management of the hosted payload accommodation contract. Rory received his degree in aeronautical engineering from Imperial College of Science and Technology in London. And in addition to his work on Gold, Rory provides program management for the remote sensing package on the NASA MAVEN Mars mission. In addition to his work as a program manager and systems engineer, Rory is an entrepreneur, an inventor, and a consummate business strategist, and we're fortunate to have him here today to discuss the role of Gold as a hosted payload on the SES Government Solutions Communications Satellite. Welcome, Rory, and I'll pass you the ball if you can.
Yeah, thanks so much.
Your screen.
Let's see if I can actually share my screen.
Great. That looks good, Rory.
All right, excellent. Okay, so here we get going. So I'm going to talk about Gold. So I think a month ago, Richard talked about Gold, and so kind of gave an overview. So I'm not going to go too much into the scientific part of Gold, but a little bit more about how Gold was developed and built, and then also a little bit of the flow from Gold from the perspective of being delivered to the spacecraft and its flow through the spacecraft assembly, integration, and test. So just sort of starting at the top, if you like, the Gold mission. So it's Gold is a NASA instrument. It stands for Global Observations of the Limb and Disk. The Gold instrument developed and built by LASP and UCF, but actually hosted on a commercial mission, SES-14, geostationary orbiting communication satellite right above Brazil. And so that spacecraft, even though it's owned and operated by SES, was built by Airbus Defense and Space in Toulouse, France, just recently launched in January of this year, and I'll talk a little bit about that. And then SES own and operate the satellite out of Betzdorf, Luxembourg. Let me just shut my office door a little bit better here. Okay. So sort of switching gear here a little bit and talking a little bit about the amount of time it takes to design and develop an instrument like Gold. In essence, we started at the tail end of 2013, and it took us approximately 4 years to go through the design development of the instrument, including the spacecraft flow to launch. And so on this image here, can you see my pointer okay? Basically, these are all the subsystems being built for the instrument. And so you can see the structure, mechanisms, optics, etc. And then once all of these are completed, it gets built up into the flight instrument down here, goes through the flight instrument testing, and then down and it gets delivered to the spacecraft, or was delivered to the spacecraft, followed the spacecraft flow to the launch site, and then launched, as I said, 25th of January this year. And currently, we're actually on orbit or in a transfer orbit, getting to the point where SES-14 will park to do its commercial communications job, and we'll start our operations and that's in the September timeframe this year. I'll talk a little bit more about that at the end. Here's kind of a more recent version of the same timeline where what you see is September, October, November, December of 2017, some of the final spacecraft testing that was going on, and then the launch campaign that was from about mid-December until mid-January for the launch. And then we're currently in this electrical transfer phase. The spacecraft will get to its orbital slot in the July timeframe. There's about 2 months of commissioning for the spacecraft, and then about a month of gold instrument commissioning before we start into the science phase. Some of the dates here are a little stale, so apologies. The launch was the 25th of January and not the 23rd. So why do we go on a commercial communication satellite? There's a huge cost savings in essentially buying a ride or hitching a ride on a commercial satellite. And so rather than paying for a dedicated satellite and procuring that satellite, what we do instead is, for a lot less money, buy a ride on a satellite that somebody's using for a different purpose but happens to be in the same orbit. This works really well for geostationary commercial communication satellites. If you're interested in looking down at the same part of the Earth all the time. And so the geostationary orbit is an orbit at which you're stationary above the surface of the Earth at about 22,000 miles and always looking down at the same spot. The commercial operators like that so that they can essentially provide service to the same part of the planet continually. In this case, it's SES-14 will serve South America, primarily Brazil, part of the eastern seaboard of the United States and across the North Atlantic. And in the images on the bottom, it shows a little bit of the history of SES Government Solutions in hosting other payloads on their commercial communication satellites, where they did CHIRP in 2011, 2 different versions of EGNOS 2012, and then more recently WAS on SES-15 and GOLD on SES-14. The little circles depict a satellite in a circle, essentially, just sort of some nice graphics to go with that. So primarily it's a cost savings to go on a commercial communication satellite. The good news is they have a lot of good capabilities for science, like they have good pointing capabilities and are able to point you very accurately at the Earth. And the other nice thing about commercial communication satellite is their purpose is to take data up and down. And so therefore they have a lot of capability to get your science data to the ground for not very expensive costs. One of the things that we encountered, and apologies, this graphic doesn't come through clearly, this is the best version I could get, but one of the things that we did encounter teaming with a commercial outfit such as SES is the commercial satellites have gone from a paradigm of chemically fueled satellites that would get to their geostationary orbit on the order of a month or two to fully electrically powered satellites that take much longer to get to their orbital slot. But essentially this approach of using fully electrical propulsion allows you to launch a much lighter spacecraft, and therefore it ends up being quite substantially cheaper launch. And so here on the left, it just shows a schematic, top left schematic of a fully chemical propulsion spacecraft. On the right, it shows a full electrical spacecraft. The mass difference is quite significant. But then on the bottom figure, it's showing the spiral orbit to the geostationary orbital slot. And as I said, it's on the order, they're saying a week on this figure. I think it's on the order of a month to be operational for a chemical propulsion mission. But for an electrical mission, it's more like 6 months. And so we're in that 6-month period right now for GOLD on SES-14, where we launched more than a month ago, but we're still on our way to that orbital slot. And as I said, the spacecraft itself starts its commissioning in the July-August timeframe. So talking a little bit more about the GOLD instrument, these are some photos of the GOLD instrument fully built, and I'll delve down a little bit more into the details. The instrument itself was designed, built, and tested by LASP here in Boulder, Colorado. The testing included thermal vacuum testing, instrument calibrations, vibration testing, shock testing, and EMI/EMC testing. Most of the testing is to make sure that the instrument will survive in the space environment, such as thermal vacuum, vibration, and shock testing. The EMI-EMC is to show that from an electrical interference standpoint that we don't interfere with the spacecraft operations or actually the launch vehicle, and vice versa. Any launch vehicle or spacecraft operations don't interfere with our operations and how we work. And then lastly, instrument calibrations are done to make sure that the instrument does that scientific experiment the way that it was planned, and that we're able to take the measurements with the right signal to noise and performance that was planned for the mission. And so delving down a little bit more into the details, I guess before I do that, I'll just point out a few features that you'll see again in subsequent slides. But these are graphite wrapped tubes there's 6 of them that are used to mount gold to the spacecraft. And then here we have light shade, and in fact, you'll see on the left picture there are 2 of those, and they're made from carbon fiber composites. They both have doors that are on a torsional spring with a latch device that's released so that those doors will open. And the purpose of the doors is to keep the instrument clean throughout the integration and test phase, which we've completed, but also as the spacecraft heats up and gets rid of any inherent contaminants on it, that they don't come back into the aperture of the instrument and we end up getting any contamination on the mirrors and affecting the measurements for gold. So moving on a little bit, gold is in fact 2 identical instruments that are built. And so here I'm showing one of the channels, and then there's another channel or instrument here. And both of these channels are attached to the outside of the electronics, which are in turn attached to these struts that are our mechanical interface to the spacecraft. In the top left, you can see the aluminum machined housings that are the instrument housing. On the top right here, you see these light shades that I pointed out in the previous picture. And then on the bottom right is the structure for the electronic box structure. And then on the left, you see it with the electronics boards actually installed into that structure. And so essentially it's 2 UV optical instruments that nest either side of electronics. It's very similar to a computer at a certain level. Our electronics have a power system, a power board, and then data system that both talks to the detectors on the instrument and commands the instrument, but also takes instrument data and sends it to the spacecraft. And so here we see, delving down a little bit more into one of the channels. At the front, we've covered, or at least at the front of the instrument from a perspective of light, we have again this carbon fiber light shade structure with an aperture door on it. And then inside, we actually have a mirror that's on a scanning mechanism that allows us to look left and right across the Earth or the disk. And so that allows the observation to start on the left-hand side of the disk and then go to the right and then repeat that job carefully. And then within the actual instrument, there is a telescope mirror, a slit, which essentially the light goes to the telescope mirror, then it goes through the slit and it splits up the light into the various wavelengths, and so hence it's a spectrograph. And then it comes off of a grating. The light splits up off of the grating. I beg your pardon. First it hits a collimator, then onto the grating, and then here is the detector assembly, which is quite involved in itself. In that on the inside it's a detector, but these detectors don't like to see air. So on the outside there's actually a vacuum door assembly that closes over the detectors and makes sure that no air gets to the detectors through handling and processing, either here at LASP or at the spacecraft facility. And then shown here, there's a number of the sub-assemblies, such as the scan mirror on the top left. This is the grating shown, and some of the other mechanisms and electronics in the board. The other fun thing about this class of detectors is they run at high voltage, and so you might ask, well, what's that? It's about 6,000 volts. So they run at super high voltages, which gives us a lot of gain, or essentially we're looking at a very faint signal and we're amplifying it thousands of times. And the manner in which that's done, you need to use a high voltage power supply, about 6,000 volts, to make that happen.
Rory, excuse me, there's one question related to the redundancy. The detectors can back each other up, but what about the electronics? Is there redundancy in the electronics?
So no, the electronics are not fully redundant. The detectors themselves have their own set of electronics, which I didn't point out, which are here. And so they each have individual electronics. They each have an individual high voltage power supply, but our primary power board and our primary data processing board are not fully redundant. That said, if one channel fails, the other channel will operate just fine. It doesn't need, channel 1 doesn't need channel 2 to operate, and vice versa, if that makes sense.
Okay, thanks.
Yeah. Okay, so that's the gold instrument, and that took took us about 12 months to go from hardware to fully built and tested. And at the beginning of 2017, we packaged up the instrument very carefully, put the instrument container inside of another container. We like to overkill things in the space business, and you get into some logical challenges with keeping other people's containers clean. So thus the box within a box. So here are shown the gold container inside of the air freight container that then was air freighted to Paris and trucked down to Airbus in Toulouse, which is about a 10, 12-hour drive. And so on the top two photos are showing the gold instrument being packaged and created in the United States. And on the bottom, essentially about 24 hours later, the instruments arriving in late at night, getting unpackaged, and our various other equipment being unpackaged to get ready to support the instrument in France. So we did standalone testing when we arrived to make sure that nothing had happened to the instrument naturally through the journey there. And we were able to do that easily. It just took us a few days. And then we actually had to wait for the spacecraft to be ready to integrate us. And that was on the order of a month or two. It's kind of normal to get there a little early and then make sure that you pass all your standalone testing and work through any problems. You hope to never have any problems, which in this case we didn't. But that's why we arrived a little earlier than they really needed us. And so then a few months later, we took the gold instrument, and it's shown here on the crane. And they're getting ready to install it on the top deck of the spacecraft, or nadir Earth pointing deck. And so that is the SES-14 spacecraft on the right, with people ready to take the instrument and integrate it onto the nadir deck. And then just a few other photos. I think probably the next one chronologically is probably the bottom right, where the instrument is coming in and it's going to get attached to the deck. The other photos are a little bit out of sequence, where we're picking it up and getting ready to place it on the spacecraft. So once we integrated on the spacecraft, so mechanically it was fastened to the spacecraft, but electrically we connected into spacecraft power supply, but also data communications lines, both commands into the instrument and then data out of the instrument to a modulator and directly to antenna. We did integrated testing and then followed the spacecraft flow. And I could probably spend about another hour or two talking through all the spacecraft testing. But luckily, our colleagues at Airbus put together a nice video of SES-14. So I'm going to attempt to play that, and hopefully that'll be a little bit more concise than me talking for an hour and a half. So let's see how I do. So let me know if this does not work, Tom. It's playing now. Good, okay. Okay, so as I said, my colleagues at Airbus did a nice job of summarizing just sort of overall the building of the SES-14 spacecraft. And so at the beginning, you saw them building up the spacecraft, and then a number of times they were showing different test configurations where the spacecraft seemed like it was actually shuddering or vibrating. It's on a special shaker table that's simulating the rocket loads, and what they do is the fully integrated spacecraft, including Gold, is going through that vibration testing to make sure that there are no surprises when we go through the actual launch on the rocket. And so the idea is you test your instrument at an instrument level all the way through all the environments, then you integrate on the spacecraft and you repeat it. When you're doing the instrument only, the goal is to make sure you don't have any problems with your instrument. When you're testing the instrument or other hardware integrated onto the spacecraft, the idea is that there are no problems between the interface of the instrument and the spacecraft, and there's nothing weird going on in the way that we talk to the spacecraft or vice versa or across power lines. And so it's important that you follow both flows in order to assure that high performance and high reliability that you need for these instruments, that they're one of a kind. We're building one Gold for one mission at this point. And we want to make sure that it's the highest quality, best performing instrument that we can get up there. So one of the other things that we ran into on SES-14 was originally we were meant to launch on a SpaceX Falcon 9 out of Cape Canaveral in Florida. And about midway through 2017, our SES colleagues informed us that it was highly likely that we would switch to go on an Ariane 5 rocket. And this is a little bit of management of portfolio by SES, where they have two satellites, SES-12 and 14. SES-12 was originally meant to launch on the Ariane 5 that we ended up launching on because it was a little bit behind schedule, more so than SES-14. And so they took SES-14 that was meant to launch on the Falcon 9 and put it on the Ariane 5 and vice versa. Overall, it was really not a big impact to us, other than we now went to French Guiana versus Cape Canaveral for launch. The specifications and the testing that we've gone through were good for all launch scenarios. Some of the provisioning of our T0 purge or nitrogen purge was a little different on the Ariane 5 than was planned on the Falcon 9. It was really more to do with logistics and less to do with capability. And so if you don't mind, I guess, traveling to French Guiana versus Cape Canaveral in Florida, there wasn't a big impact for Gold with that exception. And then I think I showed, this was in the end of the video, so this is actually then the spacecraft going into the shipping container, which is sort of an engineering feat in itself, in that the spacecraft is lifted in vertically, as you can see in the left image, and it's on a hinging interface that tips it over, and then on the other end, the lid of the container shuts. And so the plan was originally to ship the spacecraft to French Guiana do a little bit of testing, have it sit over Christmas and New Year's, and then come back in the New Year's, finish up any testing and integration, and launch. And like a lot of schedules do, things slipped a little, so we literally shipped the spacecraft to French Guiana right before the Christmas shutdown. So somewhere around the 22nd, 23rd of December, the Christmas shutdown of Arianespace. Fortunately or unfortunately for us, the spacecraft team and a few of our engineers got to work between Christmas and New Year's to support the flow at the launch facility, because there was still access into the spacecraft. And so we supported that and then finished up any testing and processing prior to the January launch. And so I was fortunate enough when I went down to support some of this that the day I arrived, the spacecraft was meant to arrive, but it slipped by a day. And so the next day I went back to the airport and actually saw the spacecraft getting unloaded off the Antonov carrier. And so here it is coming off the Antonov carrier. Once it came off the carrier, it goes on the back of a pretty large flatbed truck. They shut down the road between the airport and the Space Center, which is about a 40 or 50 mile journey, and transport the satellite to the launch facility. And so, of course, this is all done rather gingerly in a day, and there's not a lot of time to be wasted. And it was quite how do you say? It was quite impressive to be part of it and to get to watch all of that. As soon as the spacecraft got to the payload processing facility, it was taken out of the shipping container, which quickly went back to fly back to France. And then the spacecraft team, who were already in place in French Guiana, went through the various final preparations of the spacecraft getting ready for launch. And shown here is the SES-14 spacecraft. And the cone on the bottom is the actual launch adapter, which the spacecraft sits on inside of the fairing on the rocket. And so here it's going on to that fairing adapter, and then subsequently it gets integrated onto the top of the rocket with the nose cone in place. On the fairing, there's some signage, and so here you can see SES, Gold, and NASA prominently displayed. They actually put the same sticker on both sides, and on one side, some of the Gold and SES and Airbus teams had the opportunity to sign it and wish Gold and SES-14 well on its journey. And on the other side, which you'll see here in a launch video, was the logo without any signatures. So certainly some fun and some well wishes along the way for Gold here. And then, so this is showing the nose cone in place on the rocket. The final assembly of the rocket actually happens in a building. And so you can see here, it's actually inside the building, but it's a pretty sophisticated building. And on the next slide here, you can see the doors opening and the rocket actually getting ready to come out. And so the rocket rolls out of the launch assembly building to the launch tower. And how does that happen? The actual rocket itself is on a rolling transport, very large launch table, which is actually on train tracks. And so it's similar to some of the processing that used to happen on the space shuttle. In this case, it's dedicated to Ariane 5. And so on the left, the building is opening, getting ready for the Ariane 5 rocket to roll out. And then on the right, you're seeing it's in position up at the launch tower and ready to launch. Luckily for us, a lot of our team had the opportunity to go out. Some of us were actually supporting the instrument and the purge throughout the campaign and any testing that was going on. And the rest of the team were fortunate enough to come out and be part of the launch and watch it launch. And so the final part, which for me never gets old in terms of videos here, is to show the launch on the Ariane 5 rocket. So I'll go ahead and play that. So I'll try that again.
À tous de DDO, attention pour le décompte final. 10, 9, 8, 7, 6, 5, 4, 3, 2, unité Top. Allumage ultravulcan. Allumage EAP, top décollage. La propulsion est nominale.
Right, so we were very fortunate. Gold and the SES-14 satellite launched on schedule in terms of the target was had been for many months, January 25th, and you know, there's normal, let's say, challenges as you go along. And luckily, working with the Arianespace team and the Airbus team, they were able to manage the final processing and flow of the spacecraft and the launch vehicle and get it to the pad on time and get it off on time. It was a night launch, as you can see, and so it was quite spectacular. And we ended up being about 3.5 miles from the launch tower, so it was amazing to see in person. And so you might well say, well, so where is SES-14 and Gold now? Immediately after the launch, we successfully completed a quick power on and venting of the detectors in the instrument post-launch. And then we powered off the instrument, and it actually stays powered off and will remain off for the remainder of the orbit raising. Once we get through spacecraft commissioning, which will be sort of the latter part of August, we'll start the Gold commissioning. It goes for approximately 1 month, and our Gold science, or Phase E, is scheduled to start during the beginning of October of this year. And so that's when we'll start to do the Gold science and use this instrument in the manner that it was designed for, to begin the Gold scientific mission. Anyways, that's the end of the prepared materials I have. I'm certainly open for any other questions that anybody might have.
Great, thanks, Rory. Does anyone have any questions? If so, you can enter those into the chat and get those along to Rory. Just so everyone knows, we will have a couple, well, we're planning 5 or 6 of these webinars over the next few months, and we will have some additional science information for you about the Gold mission, including both aspects of the focus of Gold, which spans everything from the effects of space weather on the thermosphere and ionosphere of the Earth, and then the forcing from below, or kind of how weather affects, sort of extreme weather events also impact that region of space as well. So we'll have those upcoming over the next few months. Let's see, Rory, I don't know if you want to tackle this one from Shannon, but she asks if you could explain a little bit more about the science Gold will be studying.
Right. So yeah, I'll talk to that from my perspective. Richard may be a little bit better than me, and he talked, I guess, last month. So essentially, what Gold is looking at is the thermosphere, ionosphere. And so, if you can imagine the atmosphere around the Earth, we're looking at the influences from the sun to the to the Earth's atmosphere from the outside. But we're also looking at the effects of tidal effects and weather effects from the inside. And so by looking down at the same part of the Earth on a high cadence, on a 30-minute cadence, so basically we're measuring the whole surface every 30 minutes, we're able to look at those interactions through the atmosphere and try to understand more about the atmosphere as it changes over time on a hourly basis, essentially, versus before people have done similar science, but they were in low Earth orbits. And so they were only seeing a strip at a time. And by the time they would get back and measure the same place, it would be many hours later, in fact, maybe even a day or so later. And so we're able to get this real-time picture of what's happening to the Earth's atmosphere in perspective of the solar influences, and so geomagnetic and solar influences, but also the influences from below.
Great. Jean has asked, when will the science be available to the public from GOLD, and how will it be distributed?
Right. So I want to say that the initial data coming off the GOLD instruments will be available a few months after we start to take GOLD data, so a few months after the beginning of October this year. And in terms of its availability, that might be something we might need to get back to you. I know that it does get posted to a public archive, but on the top of my head, I can't remember the name of that.
And we will have a webinar that specifically addresses the data flow from GOLD. Karen Bryant is the Science Operations Center lead here at LASP, and she's going to present in a future webinar as well. So if you're interested in learning more about the Science Operations Center and the data flow, please stay tuned for that one as well.
So I guess we should primer for that question and make sure we address that in the next webinar.
I think she will. Another question from Doc Willie is, the observing mission is about a year. The SES-14 spacecraft will be in orbit for quite a long time. Is there any possibility of extending the mission, and what are the limiting factors,
Right.
consumables, etc.?
Right, that's an excellent question. So actually the main GOLD mission is 2 years and not 1 year. And so once we start in October of 18, it'll go for 2 years. And you're quite right. The SES-14 satellite is designed for 15, 16 years. They're saying there's even enough fuel on board to go quite a bit past the 15, 16-year mark. And so providing that we're getting good science back off of the GOLD instrument, there's certainly an opportunity to go back to NASA and ask for additional funding for an extended mission. And so we certainly hope that we're in that position as we get into the first year of the 2-year mission, that we're able to show some exciting science coming off of the GOLD instrument and the GOLD mission, and then go back to NASA and ask for extended or funding, and which it can happen. So a lot of missions are successful in extending their time frame out. There aren't any perceived limitations with the GOLD instrument. We do only design it to a 2-year mission with a design margin of 2, which means technically 4 years. But we don't anticipate there would be any issue with the GOLD instrument if you were to operate it for longer than 10 years.
Great. Any additional questions? I don't see any other questions. Well, thank you all again for joining us. We'll be back, as I mentioned earlier, we'll be back in May, probably either the last or the next to last Wednesday in May with an additional talk. And then we plan on each one of these every other month at that time. And if you want to follow with developments and updates, we do have a Facebook page at NASA GOLD Mission. Please follow along. And we work closely with our NASA heliophysics colleagues at Goddard Space Flight Center as well to put out information. And there's a @NASA Twitter account too. One final question, Rory. Does the addition of a piggybacked payload alter the lifespan of the original payload?
That's a good question. So, as these missions are designed, mass is always a big consideration. And so what's very interesting is the mass of the GOLD instrument at 42 kilos is approximately 1% of the mass of the complete completed spacecraft. And so intrinsically, it doesn't actually limit or affect the primary payload. It does take up a little space, however, on that nadir deck. And so you could have had a slightly bigger antenna reflector on that nadir deck if you didn't have gold. In terms of its impact on power or mass, there isn't a significant difference. At the same time, 1% is 1%. It costs the same amount to get the 1% to space as it did the other 99%. And so providing there's room on the spacecraft and they have the available mass, it's easy to accommodate an instrument such as gold. The larger instruments that people are looking at hosting become, I would say, more problematic in that you could have an instrument that's the whole nadir deck, and so now you're taking out an antenna and primary payload capability. So in short summary, an instrument the size of gold doesn't have a huge impact. It had no real impact on the rest of the mission, but it was designed sort of with the rest of the mission. The rest of the mission designed in the capability to host a gold instrument, I guess is the nice way to put it. So there were no compromises on the purpose of the SES-14 satellite. The primary payload, of course.
Great, thanks. You should keep talking because we're getting another question. One more from Jean. Do you see using this kind of private-public partnership with follow-on instruments in the future? Are there any plans to do so currently?
So we currently don't have another gold mission that started, but other people have started to look at this. And there's a few missions out there. I want to say one is GeoCarb, and they do have a partnership with SES also to host the GeoCarb instrument on a commercial communication satellite, or at least are looking at that. And I know that there's another instrument that was developed not too far away from LASP called Tempo, and that was developed at Ball Aerospace, and they're also looking for a commercially hosted opportunity. So it's certainly something people are looking at more and more. If you want to get to geostationary orbit and do science from there, there is a possibility to follow this path. And as I'd mentioned earlier, there was an Air Force instrument payload called CHIRP that had actually done this back in 2011. So yes, there are plans to do this in the future. We as an organization are currently always looking at other opportunities to get scientific instruments up at a lower cost, and with, I would say, more and more draws on NASA funding, it's important that we look at missions that are lower cost, and so hosted payloads do seem to be a potential path forward for a number of missions as of today.
Great. All right, well, I just put a link to the webinar webpage where we will post the video and slides from Rory's presentation today. And thanks again for joining us, everyone. Rory, thank you for your presentation and the excellent information. And we look forward to seeing you back here in May. Thanks, everyone.
Thank you very much. Appreciate it.